So we're going to do now another example of an electric circuit, and we're just going to set up the problem, get the equations of motion. We're not going to derive the full solutions, but just to go through the process. And this circuit looks very similar to what we did before, except we have more branches to deal with, so there's more individual currents. And we've also introduced this mutual inductor, which has this mutual inductance M12. And if you're wondering, what is this thing? It's a transformer. So when you have a current in one branch, it will induce a current in another branch. And so we can now proceed with defining the terms exactly as we did before. So we have inductors L1, L2, and L3. And so I will write down the energy of my inductors. So I have a 1/2 L1, and that has a current of Q3 dot. And then I also have a 1/2 L2 plus L3, Q4 dot. And the difference now is that I have this mutual inductance. So I have an M12, and we have the current through here, which is Q3 dot, Q4 dot. And so this is probably the first time that you will have seen something that's quadratic with two different velocities, generalized velocities involved. So before, we've always had terms like x dot squared, y dot squared, and so on. This would be the equivalent of a velocity in one direction times the velocity in a second direction. So this is for our inductors. So these are like the kinetic energy terms. And then we can write down the energies in the capacitors, which are our potential energy terms. So we have two capacitors in the circuit, C1 and C2. So I have a 1/2 C1, and it will be Q2 squared, because that will be the charge on this branch. And then the second circuit, 1/2 C2 Q4 squared. And then I come to my resistors, and there's two resistors in the circuit, R1 and R2. So these act as dissipative forces. So let's look at this branch. So that's a minus R1 Q2 dot is my generalized force there. And in this branch, I would have a Q4 minus R2 Q4 dot. Okay, so those are the terms. Oh, and I have the battery, of course, which I have forgot. And so that's the energy in the battery is minus EQ1. And we have a constraint at the junctions. So Q1 has to be equal to Q2 plus Q3 dots. So Q1 dot equal to Q2 dot plus Q3 dot. And that's the only constraint. This is a total differential. And so I have that the charge has to be conserved. And with that constraint, I can then eliminate one of the generalized coordinates. So my generalized coordinates, Q1, Q2, Q3, and Q4, but subject to this constraint. There's one constraint equation, so I can eliminate one of the coordinates, and I will just choose to eliminate Q1. And so finally, I collect everything together and can write down the Lagrangian. So I will just write that here, L1 Q3 dot squared plus a 1/2 into L2, no, sorry, that's L, oh yes, right, L1 plus L2 Q4 dot squared. Let's make sure oh no, that should be a 2 plus 3. Okay. L2 plus L3 Q4 dot squared. I have my mutual inductance, M12 Q3 dot Q4 dot. And okay, so these are my kinetic energy terms, and then this is the potential energy term. So I have a minus 1 over 2 C1 Q2 squared minus 1 over 2 C2 Q4 squared. And then I also have this term from the battery, which is in terms of Q1. And so I would have to add E Q2 plus Q3. And so this is my Lagrangian. So it's long, it's a little bit complicated with the 3 variables, 2Q, Q2, Q3, and Q4, but should be straightforward then to analyze.